Hi, and welcome to Mike Likes Robots, where we share knowledge to accelerate robotics. The past couple of days I've been recording without the face cam, but I'm back, and we're ready to attempt day 16 of the Advent of Code challenge in Rust. So let's open it up and take a look. We're looking at day 16, Reindeer Maze. I'll read this out. Feel free to skip ahead using the chapters if you have already seen the puzzle. Day 16, Reindeer Maze. It's time again for the Reindeer Olympics. This year, the big event is the Reindeer Maze, where the reindeer compete for the lowest score. You and the historians arrive to search for the chief right as the event is about to start. It wouldn't hurt to watch a little, right? The reindeer start on the start tile, marked S, facing east and need to reach the end tile, marked E. They can move forward one tile at a time, increasing their score by 1 point, but never into a wall, which is a hash. They can also rotate clockwise or counterclockwise 90 degrees at a time, increasing their score by 1,000 points. To figure out the best place to sit, you start by grabbing a map, your puzzle input, from a nearby kiosk. For example, it gives an example here. There are many paths through this maze, but taking any of the best paths would incur a score of only 7,036. This can be achieved by taking a total of 36 steps forward and turning 90 degrees a total of 7 times. There's 2 examples given. In this maze, the best paths cost 11,048 points. Following one such path would look like this, and then it gives us another example here. Note that the path shown above includes one 90-degree turn as the very first move, rotating the reindeer from facing east to facing north. Analyze your map carefully. What is the lowest score a reindeer could possibly get? Okay, so this is a pretty simple, well, I say that, but I think I know how to solve it straight away. So we're going to we're basically going to flood fill every possible solution and then take the one with the minimum token cost. Now, normally when I do this kind of flood filling, I wouldn't take account 90-degree turns. I would just assume it's free to step in a particular direction. So that might make it a little more tricky to code. So what I'm going to do now is create the project and cut to when it's ready to go. Okay, here we are. And the main function is printing hello world. We've got an empty struct called the reindeer maze and 2 test texts, which come from the Advent of Code examples. We've also got 2 unit tests that include those 2 texts and check that they are the right numbers given by the puzzle. So with that in place, I'm now going to start to read in the puzzle into the reindeer maze structure. I think how I want to do this is to create an enum for the types of cell that are available. So there will be a wall, there will be the end, and maybe the start, although I think I might include that in the reindeer maze structure. Okay, now we're going to include, we might actually be better off with a grid and then say what is in it. Let's do that. Okay, so it's going to be a grid with a vec of maze cells. Then within that, we're going to have the reindeer position, which will be a point. And again, the point we are going to take from our util crate. Util equals point. Point. There we go. Oh, it should be a comma. There we go. Okay, so we've got a grid with our maze cells. We've got our point position. I think we can also encode the start as another maze cell type. Right, now I'm also going to include an enum for the reindeer maze error. That's going to be for the different error types. So I think that will be, for example, no start found, no end found, and no reindeer found. Now I've already got a few things starting to appear on the page, so I'm going to separate these out into different files. I'm sure most of them will be pretty simple, but I'd like to keep the code clean. The reindeer maze, and then we need the maze, reindeer maze error. Okay, we'll declare modules for all of these. Module maze cell, module reindeer maze, and module reindeer maze error. Grab this maze cell and put it into here. Grab the error enum and put it into here. And I can make this public, as well as this public. And then the reindeer maze will be taken from main. Now we can start to implement the rest of our reading in code from here. Reindeer maze is private, so we're going to make that public. And then when we do implement a part A function, we'll make that public. Okay, so far, we don't need this. And we should be in good shape. So with the structures and enums created, I'm now going to implement from string for reindeer maze. The error type will be the reindeer maze error. And then we can autocomplete from str. And firstly, I'm just going to autocomplete, or rather, I'm just going to return the empty structure. So the grid will be an empty vector, and the reindeer position will be a point containing 0, 0. I'll rename this to puzzle. There we go. So we should now have from string available. We need to make sure that's in scope. Yes. So reindeer maze, copy and paste that. Is that happier? Doesn't implement debug. Okay. Reindeer maze error needs derive debug on it. I think we can also derive debug on the maze cell and on the maze itself. Okay, now we don't have a part A function. So let's do that. Simple reindeer maze pub function part A takes a reference to self and returns a usize, which will be 0 to begin with. Okay, now everything compiles. We should be able to run a test and get 2 failures. Let's go ahead and parse that puzzle. So the puzzle looks like this. So we can pretty simply say for col index col row index row in puzzle.lines.enumerate for col index cell in row.cars.enumerate. We're just going to match on the cell. We can create a point actually. Let point is a point of row index as i32 and col index as i32. There we go. Now we're going to match on this cell. We can already create a new error type, unrecognized maze car. So in my default case, if I receive something I'm not expecting, I can give it the unrecognized maze car. Okay. So we know we've got hash, e, s, and dot to look out for. Let's code all of those in. We've got a hash, we've got an e, We've got a dot. And we've got an S. We don't actually need the point in this case. We can just look at the grid to get the point out. So yeah, we don't need to do this. Let's get rid of this. We don't need the point. I'll just comment it out because we will need it when we're defining the reindeer position. So I'll keep let mute reindeer pos equals none. Then when we get the reindeer, it's here. Then it will be a reindeer pos will become sum of this point. Now we don't need any of that. Okay. That's fine. Our dot, we can just push empty onto our maze cell. So let mute grid is a vector. When we reach the end of this outer for loop, we'll grid.push row. And let's mute. Wait, we don't want to push row. We want to push. Actually, we can do that. Let's change this to, because we do need the index and we need the row. Okay. I'll just recall this maze row. That'll be a vector. And then we'll push it into the grid. So that's every time we go over a line, we create a row to store the data. And then for each character within the line, we're going to push a cell into that vector. So in this case, we actually do want to push something. We want to push that it's a start point. So we're going to push maze row dot push maze cell starts. There we go. In this case, we're going to do that, the maze row dot push maze cell empty. In this case, it is the end. And in this case, it is a wall. Okay. Now, I don't strictly need to do this, but I'm going to do it anyway for safety. I just want to check that the puzzle has a start and an end. So for this, I'm going to... I can just check if reindeer position is found, right? No reindeer found and no start found are the same thing. So I don't need to track that one. I can remove that. Start found is gone. And then for end, we put a semicolon here and we do end found equals true. So at the end of this, if reindeer pos dot is none, then we can return an error of reindeer maze error, no start found. If not end found, then we'll return an error for that. And there we go, that's our error cases checked. Now we just need to actually construct the right object, which in this case will be a grid. And in this case, we can just do let reindeer pos is equal to reindeer pos.unwrap, because we've just checked that it is none. At that point, we can remove it from here. Okay, that's our puzzle completely parsed. I will probably need to write the code to print it out again at some point. For now, I'm just going to try and implement the solution. So I think from the puzzle, you're allowed to turn 90 degrees, and it can be left or right. Yes. And turning left is the same cost as turning right, so I can't just turn right 3 times and expect it to be the same thing. So for this, I'm going to create a new function. It will be the solve, I guess, or find cheapest. It will take an and self, and it will take some other stuff too that we have yet to find. So this will be recursive. It's the simplest thing to do. We are going to need to check in the current direction. So let's take our direction as a direction. There it is. We'll make it a direction reference. We'll give it 0 just so it compiles. Okay, so now we know what way we're facing, so we should try and go in all directions. And track where we've been. There is a potential problem, which, yeah, it is possible that we have loops. So we need to be able to check that we've not gotten back onto the same path as we've already done. So for that reason, I'm going to say there's a visited, which will be a mutable hash set. Actually, I think it can just be a hash set of points that we visited already. Let's import that. So we are first going to try and go forwards. Now, we do want to be trying to go in all directions to make sure that we've explored everything. So let's try and go forwards first of all. So candidate equals. We should know what current point we are, but I guess we can take the top of visited for that. Well, visited doesn't need to be a hash set; it can be a vector, so we can take the top of it. Visited dot back last. Now this is an option. I think we can go ahead and assume that we have at least the starting point. Okay, so we're passed in a vector. It's got our current visited entries. So we'll try and go forwards. We'll check if that point has been checked already. So if visited.contains candidate, we can just straight away return. 0 doesn't make sense. I think we're going to need a current token count. This may, in fact, be an option to say that it works. But even if we find the same point, we might have found a cheaper route to the same point. So maybe we need to check that we've got the cheapest route to the same point so far. At which point our visited actually becomes a point and a token count, which will be a usize. Now we can't just check if visited contains, we have to find, we need to iter. Can we find all? No. I think we've been going for a little while, so this coding isn't going to be done in the next 5 minutes. So I'm going to cut here and return once I have completed more of the code. So here I am with a working solution for part 1. And wow, did it take me a long time. I think it must have taken a full day, maybe? Maybe not quite, but it was quite a bit more complicated than I was expecting. So let me take you through what I've done. The 3 stages, the 3 solutions that I've built. So first, main is pretty simple. It's just putting in the input.txt and then running the solution on it. Maze cell is also pretty simple. It's just a few possibilities of what's inside. And then maze error is, again, pretty simple, pretty much as I left it from the earlier part of the video. Now, reindeer maze was my first attempt at solving this problem. It's pretty similar to what it was before. The parsing is the same, it's just how to solve the problem. So what I started doing was I made a find cheapest function, which was going to be recursive. And I started building it recursive before switching over to iterative. So for a time I had both methods so that I could sort of compare between them. I never renamed the iterative method. It's fine. It doesn't need to be there, but it's fine. So how this is working is that it will keep a vector of points. So a list of possible paths that it's so far taken through the maze. So it will start with the initial position, the start position, and then it will figure out which directions it's able to travel in. So in the case of test small, from the bottom left, it can travel up and it can travel right. So it's going to push 2 new possible paths to the candidates vector. One will be the start position plus the one to its right, and then the other will be the start position plus the one to the top. Then it will repeatedly take a path from the candidates and explore it further. And it will keep doing that, and it will keep doing that until it reaches the end position, or it meets a wall and it's already visited that place. Because as you track the path you've gone along, you can check whether you've already been there to defeat loops. So this actually does work. This solution works. And I can show that by running these tests. In fact, I can just run it with this button here. And all 3 passed. And that's the 2 test examples that came with the puzzle, plus my own test very small, which I used to help develop the algorithm when it wasn't doing what I expected. And here is just literally 1 possible path to the right and then 1 possible path up that goes to the end. So that was useful to help develop. I'm trying to think if there's anything useful to show within this iterative function. So if it finds an endpoint, it will figure out the minimum cost based on the previous minimum cost, if any, minned with the new cost that's been found. So to be able to find that, it uses the path cost function. Now the idea here is that it's not tracking the direction that it's going, right? It's finding a possible route to the end and then figuring out what turns it needs to make in order to do that route. And that's done within the path cost function. So overall, this while loop becomes take the latest path, check if it's at the end already. If it is, check what the cost of that path is, and if it's lower than a previous one, save it to the min cost. If it's not at the end, figure out what possible points you can go to from the end of that path, and then add that to the candidates. And then by doing that, you either remove candidates when they reach a dead end or when they reach the end. And that will leave candidates empty, so that when you try to do while let sum, it will reach the end of this while loop and just return min cost. Let me show you these other functions. They're also fairly simple. So for possible points, it takes my horiz and vert method from direction, which gives a vector of directions left, up, right, and down. It then does a filter map. It says, hey, take the current point, add the direction to it, and check if A, you haven't visited it, and B, whether it's empty or the end. If it's empty or the end, that means it's a valid place to go to. If, however, it's any other option, then it's not a valid place to go to. So you return none. So this filter map says, if I get some back, unwrap it. If I get none back, ignore it. And then when I do this collect, I end up with an array of the points that are possible to travel to from the point I've got that have not been visited before. That's how that function works. And then path cost is also fairly simple. What happens is it does a simple check that it's getting something valid, and then it will go through the entire list and figure out what direction it is based on the previous point. If it's the same direction that it's currently facing, it adds 1. If it's a 90-degree right turn from its previous direction, then it will add 1,000 for the right angle turn plus 1 for the step it took. And finally, the same logic for the left turn. I've left out going backwards here because that would mean going back along the path it's come from, which it's already visited, so it wouldn't work. So that's it. That's the reindeer maze solution, an iterative solution which finds all the paths, finds all the costs for those paths, and checks the minimum one. Now, the problem comes when you run it, because the full input text is very, very big. And I ran it and it just sat there thinking. So after that, I decided to optimize it a bit. I tried to create a solution where instead of checking every single empty space, it only saves the junctions. So by that, I mean this start point is a junction between this path and this path going up. Now you can check whether something's a path if it only has one point, so it's a dead end, such as this one, or it's got 3 or more points it can go to in left, right, up, and down. Because if it can go in 3 directions, like, where's an example here? I'm not sure this one has an example. Ah, here's one, right. So it's got 3 directions it can go in, up, down, and left. So that means it is a junction between those paths. Also, if it can go in any direction, which I did see an example of, but you get the idea. It can go left, right, up, and down, so it's a junction. If it only has 2 paths, you need to check whether they're in a line. So take this, it can go left, and it can go right. Those are on the same line, so it's not a junction. It's just along an already existing path. If you get a corner piece, that means you found a right angle, and that makes it a junction. You need to change direction. So the junction maze is very similar to the reindeer maze, except that after finding the initial grid, it then builds a hash set of junctions that exist. Then, to do that, it counts how many neighbors it has. If the length is not 2, insert it because it's a junction. If it is 2, then check the direction between them. And if it has some direction, I've put here, because I have a direction of function. The direction of function says if it's right or up or left or down, or the diagonal pieces as well. So in this case, if you have a point, if you're checking a point and you've got a point below and a point to the right, meaning that this point is a right angle, then the direction between these two will be diagonal. So it will be some direction. However, if you have a point and there's a point below it and above it, then when you try to do the direction from this one to this one, it's not exactly one different, which means it returns none from the direction of, which is why if it is some, then it's a right angle, not a straight line. So that's how that works. So once we have a hash set of the possible junctions, it then changes 2 functions. It changes the path cost and it changes the possible points. Because when you're going through the possible points, you need to figure out if you're already at a wall, let's say, then that's not a possible point to go to. However, if you get to an empty space in the direction, in a particular direction, you should keep going that direction until you hit a junction. And that's how you travel a whole path at once. So in this case, from the start point, we try to go upwards. Now, this isn't a junction, so there's no point checking it by itself. Instead, we can keep going in the up direction until we reach a junction, which would be this one. From then, we can check all the paths going up from it and all the paths going right from it. So by doing that, you eliminate all the points along the paths that don't have multiple directions to go in. Now, I actually don't know if this improved it at all, because when I ran it against the test cases, it worked practically immediately. And when I ran it against the input cases, it ran forever. I mean, I'm sure it would terminate at some point because it has a termination built in, as we've shown by the test cases, but it's not finishing in any decent amount of time. So my optimization with FloodFill still wasn't successful. That's when I started building my third solution, which is the reindeer graph. There is an algorithm. I think I can delete this now. There's an algorithm called Dijkstra's algorithm. In fact, there's multiple graph searching algorithms, of which Dijkstra's is one. And Dijkstra's is great for finding the shortest path between 2 points. To do it, you need to build a graph that is a node that is connected to some other nodes. And you also need to know the path cost. So I thought that it actually wasn't possible to do Dijkstra's algorithm because of the turning logic. You needed to know what direction you were turning in before you would be able to use this algorithm. And because the node doesn't inherently code which direction you're facing, there wouldn't be a way to encode that path cost. It turns out that I was wrong. So I did implement this solution. In fact, I used pretty much all the code from the reindeer junction maze. What I did was I created the initial grid of all the maze cell values. Then I went through and found the junctions. So now I've got all the junctions, and the junctions form the nodes in the graph. So this start point is a node, this point is a node, this point is a node. And by doing that, you can plot a path of nodes all the way to the end. Back to the reindeer graph, there it is. So once we've built the set of junctions, we then need to build the graphs. And essentially what happens is, if you reach a junction, then you should add the right turn score. Now, I wasn't sure if this would work, but it did work. In fact, I'm having trouble thinking how to explain it. So it builds the map of junctions, then it iterates over that set of junctions, and for each one figures out what other junctions it can reach. To figure that out, it says, am I in a straight line to this point? If I am, I'm going to iterate along it and check that I don't find a wall. If I don't find a wall, that means it's possible. It is on a reachable path. By doing that, we create a list of reachables for every junction point, and then our graph solution can take the start point. For every node that it's at, it needs a function to determine what it can reach and what the cost is. So we can just check what the hash map entry is for that we just built, the reachable array. And then if it's at the end, then that is the termination condition. So by doing that, and I coded 2 methods of figuring out the path. First, I wasn't convinced that what I'd done actually represented the true cost of the graph. So first, I encoded everything with a path cost of 1. And when I did that, I got the wrong solution because I would get the actual shortest path back without accounting for changes in direction. And then I would figure out the path cost. So this path cost is essentially the same function as in Reindeer Junction Maze. it just figures out if it's in the same direction, return the difference. Otherwise, make a right angle turn, 1,000 points, and then add the difference. So that it's pretty simple. It's pretty similar to Reindeer Maze. Okay, so my two methods of calculating the cost. One is return the whole graph and then figure out the path cost from it using the path cost function. And the second is that the Dijkstra's algorithm actually returns the cost that it calculated while finding the endpoint. So I can directly use that. And when I tested this, those two numbers were identical. So by building in the path cost in the from string function, by building in the path cost as 1,000 plus the change in junctions, that actually worked correctly. So at this point, I was able to run it, and although it was not instant, and I'll show you how long it takes here, I won't cut this bit, this is real runtime. There we go, so it took maybe 2.5 seconds, something like that. In fact, we can run it again in release mode and see how much faster it is. That was about 1 second, I think, roughly speaking. And this 83444 is the correct answer. So there we have part 1 finished. It took me a long time. I worked pretty hard on it. And with that in mind, I don't know whether I'll be able to even finish the Advent of Code challenge. I'll get as far as I can, but I may not be able to get up to 25. I've never finished the challenge before. Okay, with that said, is there anything left to say about this? 3 possible solutions all work. Only the graph solution works for finding the full path cost. And I think that's all there is to mention about it. So, let's take a look at part 2. I'll read it out. Feel free to skip ahead. There are chapters in the description. Now that you know what the best paths look like, you can figure out the best spot to sit. Every non-wall tile, S, dot, or E, is equipped with places to sit along the edges of the tile. While determining which of these tiles would be the best spot to sit depends on a whole bunch of factors: how comfortable the seats are, how far away the bathrooms are, whether there's a pillar blocking your view, etc. The most important factor is whether the tile is on one of the best paths through the maze. If you sit somewhere else, you'd miss all the action. So, you'll need to determine which tiles are part of any best path through the maze, including the S and E tiles. In the first example, there are 45 tiles marked O that are part of at least one of the various best paths through the maze. Here we go, there are multiple best paths possible. In the second example, there are 64 tiles that are part of at least one of the best paths. So we're not taking account of any point changes in direction anymore. It is literally just find the best path and then count how many tiles are on those combined best paths. Analyze your map further. How many tiles are part of at least one of the best paths through the maze? So I've already read through this. I have a theory about how to do this. I don't know how well it's going to work. So my theory is this. I will solve... The problem is that my Dijkstra's algorithm implementation, which is from a crate, doesn't return all the possible paths from the start to the end with the minimum cost. It returns one path from the start to the end with the minimum cost. So in order to find all the best possible paths, I need to essentially solve it multiple times. Now, one idea I had was that I try and break a link in the middle. Let's say this link. If I can calculate the algorithm multiple times, except the first time this is possible, this transition, and then the second time I break this link so it's not possible to traverse, then the algorithm will automatically move along this path instead, because the first path isn't possible. However, it's not as simple to just pick a point in the middle and break the chain, right? you're not certain to get all the paths that way. You're not certain to even get a new solution that way. So my next theory was to take the list of junctions from the end to the start, and then for each one, break the chain and see if it is possible to reach the end. So let's take this junction here. So I can say this is the end node. Now I'm going to go to the start node, and I'm going to break that chain. Is it possible to reach the end? No. So I go back here and I break this chain. Is it possible to reach the end? Yes, I have an alternate solution here. So that should give me another solution. But I think the trouble then is that I have to break it for every subsequent chain that I find that has the same minimum cost. So far I don't have a good answer of how to find all of the possible paths with the same minimum cost. Another idea is to take a look at the Dijkstra's algorithm again. And here we are. This is the crate that I was looking at. So I use this Dijkstra, and I've shown it to you in my code. This is just to compute the shortest path. However, is there a way to get multiple different solutions with the shortest path? Now, Dijkstra all will find all the possible nodes it's possible to reach from a given start point. So I could hand it my start and see how many of the possible solutions have the end node in. But this will take roughly the same time as doing my flood fill with junction, right? It's the reindeer junction maze, but built by the Dijkstra all algorithm instead of by me. I don't think this is going to help at all. There's Dijkstra partial. So from here, I can figure out the reachable nodes from a starting point and the minimum cost to reach them. This actually might be a possible solution. I haven't looked at this very well. I can't think of a way to use the Dijkstra partial algorithm, so I'm going to move on to Dijkstra reach. So this will give me one entry that reaches the end and one possible path to it. So again, I don't think that's going to work. So at this point, I'm going to cut. I don't think I have a good way of working this out, and I'm going to try and code this. I'll figure out a solution and try and code it, and then I will resume once I have something to show. So I'm back with a working solution, and again, it took a long time. Not a day this time, thankfully, or anywhere near it, but definitely a long time. So my epiphany, or research rather, led me to a new method called yen. At first, I decided to try and copy the Dijkstra algorithm from the crate because it was open source, and try and modify it so it would find multiple paths and iterate over increasingly long paths until it found one, so that I could just keep taking until the path cost went up. And when I was trying to copy the Dijkstra algorithm, I realized that there was a whole crate of other pathfinding methods in there. So it was while looking through the pathfinding crate that I found yen. Now, yen is essentially Dijkstra, except you provide a number of shortest paths that you want to find. So it will find k shortest paths, which is cool. I don't know how many paths I want to find. I just want to keep finding. So in the end, what I did was I did a path count and I just guessed how many paths there might be. So I found there's somewhere between 10 and 20 paths, I think it is. So we never get up to 30, 40, 50. But in any case, if you put too many in at once, you'll end up computing loads of paths you don't need. And if you put in too few, then you'll end up recomputing the same path over and over. So I could now say, well, I know there's around 15, so compute 15 paths. But this is how I solved it to begin with, so I am going to leave it like this. It doesn't take too long to run, especially in release mode. Now, that all sounds simple enough, because it assumes that what I had before was correct, which is that having 1,000 cost for every change of junction is correct. When I first wrote this, I got the wrong answer back. And I guessed correctly, as it turns out, that it was because my solution, my original Dijkstra's algorithm was not correct, because my node or my edge costs were not correct. So I changed how it works. Now, instead of having a point and another point where it guesses the amount in between, based on assuming there's a turn and then adding the difference in the point values, now my node contains both the direction I'm currently facing and the point in the grid that I am sitting on. By doing that, I can say possible ways to go from 0, 0 facing right is 0, 0 facing down at a cost of 100, 0, 0 facing up at a cost of 100, and 1, 0 at a cost of 1 facing right. So by doing that, every node has 4 possibilities that it can go to, right? It can go forwards, or it can, actually 3 possibilities. So it can go forwards, or it can turn left or right. Forwards is a cost of 1, left and right are a cost of 1,000. Now it gets more complicated in that I wanted to optimize it to continue using junctions. So I've still got my junctions set here. So what I do instead is for a node, I add the left and the right turn. And then for the forward turn, I keep going until I hit a junction, and I add that node instead. So instead of 0, 0 going to 0, 1, if there's a 0, 2 that's empty, it will go to 0, 2. If there's a 0, 3 that's empty, it will go to 0, 3, and so on. And instead, it will have the difference as an edge cost. So by doing that, which took quite a bit of effort, I was able to get a fully working solution. So now my part A is verifiably correct instead of just happening to be correct, and my part B produces the correct solution. So all of this code I'll make available online. Unfortunately, I have deleted all my code in an attempt to get it working properly for the initial attempt at part A, but the other attempts are still there, and you saw what the code was during the video. This is a more correct method. It is better. So I'm going to stop here. I will commit the code and push it to GitHub. I don't think I'll be able to catch up to the current day in Advent of Code, which means this series will go on longer than Christmas, which is fine. I'll go as far as I can. I think at some point the puzzles will just be too difficult for me, but we'll see how far I can get. So thank you for watching, and I'll see you tomorrow for the day 17 attempt. See you then.